rigid.
Who taught that one?
Paul Jagdinsky.
Okay, yeah.
I couldn't. I would just put on the lecture for attendance and then just like look at something, like try and figure it out during homework and stuff. Like it was so bad I couldn't get it.
This is a viable structure. This is a viable structure. This is a viable structure. So there's multiple ones here you can do. There's a bunch of them. As long as you have two, actually, hold on. Nope, this is not a viable structure. Never mind. Those ones are not. What's wrong with those ones?
Shouldn't there only, wait.
There's no sp3 carbon in those ones.
Yeah.
So we can't do those. But you could do, hold on, let me try that again. 1, 2, oh, come on. Yeah, you can't arrange these in any way that would have it. So this is probably, that one's your only reasonable one that you can do. Does that make sense why those ones are bad? You didn't have any sp3 carbons in those. How do you show an sp2 and a, what do you mean, Skylar? Like, how do I draw them, or what's the representation on the IR? I want to make sure I understand your question correctly. Okay. Are you guys okay with this one here that I drew? It has, and I will draw it. I'm going to scroll down a little bit. And I want to clear, try that again. So when I draw this, I have an alcohol, right? Which I said I had to have. I have sp2 carbons, right? That's here, correct? And I have sp3 carbons, which I said I had to have here. Does that make sense? Do you guys see all of those from my IR? Okay, nope. You're welcome. Yep, and remember, if you're ever unsure about something, don't hesitate to send me, send a chat or something, or speak up and say, I literally don't know where you're drawing this or something. So another thing you could do, it looks really weird, but if you want to draw this, I suppose it would be correct, would be if you drew like that. That technically would be, it looks really weird, like you have a carbon here in the middle. That's the thing, it just looks weird, but that technically wouldn't be wrong either. Don't recommend it. All right. It's kind of weird because a bunch of you got up and started moving through your apartments at the same time.
I'm making tea.
Yeah, I had to get a snack, but I didn't want to miss anything.
Okay, so go ahead and work on this one for 3. Suggest a structure for compound C, C4H8O2. Mag, are you talking to strangers? What have I told you about talking to strangers?
No, I'm not. I want to show you my bunny.
Ooh.
Come here, Soot. Look, she's so cute.
I love that. And now I love one.
She loves to eat a lot.
Same. But I think you guys know that. Gwen, do you remember that time you, me, and Ellie went to go get burgers?
Yeah.
Bella, do you remember that time we grabbed lunch in the Union?
Remember.
I wasn't there. I couldn't go.
Oh, that's right. It was
Yeah, they 3 went without me because I had another class.
Tamina, Lena, and Why do I
I
keep forgetting?
forget, I don't remember her name
I
either.
think you and Ellie got Einstein's one time too.
Yes, and we also had Chipotle.
Chipotle. That was the best office hours in the world.
Hey, you guys should have come by my office hours. I had food.
I should have. I remember I had a class like right after Chem, so I could never join you guys, and I was all sad.
I also had so many of you get crippled by my desk. I know Gwen definitely took a header to that desk.
Oh my god. I literally hit my knee on that. Like,
If I stayed there longer, I would have got padding for that desk because so many of you left with a head injury or a leg injury.
oh yeah. And the shelving.
Yeah, because it's like, boom. I mean, you shrugged it off like a champ.
Yeah. The same thing happens to me in my apartment because I have like one of those fridges where it's like the freezer on the top and the fridge on the bottom. And sometimes I'll be in the fridge and then I'll sit up and forget the freezer is there and just bam, I'm like on the back of my head. It hurts so bad.
I don't have a pet, so unfortunately I can't show you anything cool.
I have a question.
Mhm.
That really big like dip past or peak past the double bond of carbon and oxygen, is that like considered the fingerprint region?
Yeah. What did she tell you guys? 15 or 1400, something like that? Basically around 15 or 1400. Every professor has like their own like demarcation. Mine's 1400. So if you're 1400 or to the right, that's the fingerprint region.
So I know like last night you mentioned there's not really much anything useful because it's unique to every molecule, right?
There are things there. It's just it's kind of like identify your molecule first and come up with something and then see if there are things there that can kind of back it up.
Okay.
Because go ahead.
Because we already know like what the molecule is or like the compound, do we necessarily have to look into the
You don't need to, but you could find something though that backs up your things if you want a little bit more evidence.
Okay.
Does that make sense?
Yeah.
It's kind of like if you're writing a research paper, the peaks outside of the hour region are like your journal articles and your books and stuff like that. And then the fingerprint region would be things like interviews or TV episode references. Like they can be useful, but they're not as like trustworthy.
Okay, yeah, that makes sense.
Never trust fingerprints. As a forensic scientist, I can tell you don't trust fingerprints. Fun fact, koalas have identical fingerprints to humans. In a crime scene in Australia that was once overrun by koalas, they thought that like 30 people had participated in a murder. Turns out it was just koalas. Okay, so do you guys see here? I drew the 3000 line. I saw the double bonded oxygen, right? Those are the two things that pop out at me. And then I did my degrees of unsaturation and I get one. So I have one double bond, but thankfully I have a carbonyl that accounts for my double bond, right? So I meet my degrees of unsaturation. So I'm going to have double bonded O. Then I'm going to have O. That would be a reasonable structure. So a ester would be my functional group. Do you guys see where I got that ester from? Are you guys okay with that? So I think, who was that? Mag, was that you that was asking me about the fingerprint region?
No, that was me.
Okay, Morgan. I think that this is a carbon single bonded to oxygen in the fingerprint region. So if you looked it up, this is what that is, but it's not reliable.
Carbon double bonded to oxygen.
Sorry, carbon single bonded to oxygen.
Oh, okay.
I believe. You would have to double check that. I really don't know my IR region, my fingerprint region all that well anymore because I don't use it. I don't do real science anymore.
It's okay. I don't know it either. I'm looking at my chart.
Twinsies. Okay. Oh, snap. It's Cole. Cole, how's it going, buddy?
It's going good. How about you?
Good. It's good to see you guys. All right. So does that make sense for our molecule? Are you guys okay with that? All right. So this is why if you can use up your degrees of unsaturation, you're like, well, there's a carbonyl that has to be it. Makes life easier. Okay. There's a couple other ways we could have drawn that structure. Like we don't have to have it that way. That's just one of the ways we could have done it. Okay. All right. 7.
Can you look at mine real quick if I hold it up to the camera?
Yeah. Let me just scroll down to yours. Yep, that works.
Thank you.
You're welcome. Okay, complete the following acid-base reactions by doing the following. Label the acid, label the base, add curly arrows to show the proton transfer, draw the conjugate acid and conjugate base, give approximate pKa values. Have you guys done acid-base chemistry for this? Is this the question?
Yes, but I don't understand the pKa, and I don't understand.
No, we
She
did-
lost me for the entire week.
Oh yeah, I feel like we did this like particular thing for like 20 minutes, and then that was it.
Okay, pKa is the relative strength of how easy it is to take off your proton, basically how acidic it is. The lower the pKa, the more acidic it is. So if I think about hydroiodic acid, I'm gonna just draw that here, HI, which is our strongest halogen acid. Does anyone know what the pKa of this is? It's about -11. Water is about 16. If you had something like an alkane, this is about 50. So everything has a pKa when it comes to a proton, right? So basically you just kind of have to label what the relative strength of the pKa is. Does anyone know what the pKa is of an alkyne? Or you guys have no clue?
25.
It is 25 on the dot. That is that proton coming off here. So in our first thing, which one is our acid? The one on the left or the one on the right?
Right.
Yes, because why is the one, what's the key indicator that the one on the left is not an acid?
Because it's taking a proton, not donating it.
It has a negative charge too. It's usually a good indicator that it's not an acid. That's an easy thing to watch out for. So this is going to be my base. This is going to be my acid, right? So if a nitrogen has a negative charge, how many bonds and lone pairs does it have?
Doesn't it have 6? Right, like 6 electrons because it has 5 valence electrons.
No, if it has, it's still going to have the full octet, but this nitrogen here is going to have how many bonds and how many lone pairs?
It's gonna
2
have
for both.
4.
It's going to have 2 bonds and 2 lone pairs. If a nitrogen has a negative charge, it has 2 bonds and 2 lone pairs. That's your key indicator. So if something is your base, in order to be a base, what does it need to have? That I just drew on that nitrogen. A lone pair. If your molecule doesn't have a lone pair, it can't be a base. This is also another way to tell that this is your acid. There's no lone pair on any of those atoms, right? Carbons don't have lone pairs typically. So this is the easy way to tell that right there that that's your acid because it doesn't have a lone pair. So my nitrogen is simply going to take this proton and this bond is going to go back onto that. Like that. All right, so then the conjugate acid, the base becomes the conjugate acid. So now all I'm going to do is just draw that, except now that nitrogen has a hydrogen on it. That's the easy way to tell that. Okay. The conjugate base was the acid. So you draw the same thing, except now where the hydrogen was, you put a lone pair. What is missing from this compound? Oh, there's also a lone pair here. What's missing from my arrow pushing, one of the rules I gave you at the beginning? Always conserve.
The charge.
Yep, so where does my negative charge belong? On my conjugate acid or my conjugate base?
The base.
Conjugate base, my negative charge is going to be on this carbon. What questions do you guys have about acid-base reactions?
Okay, I'm so confused now because I just did this problem with my tutor like earlier today, and basically we did the same thing, but instead of like putting a lone pair and a negative charge, we put a positive charge. And it's probably wrong, but he told me it's right, so now I'm just kind of confused.
You can trust whoever you want, the tutor or the person. One second. The person with a PhD from a top 10 university.
It's okay.
Who to trust.
Okay.
So when you take a proton from somewhere, you leave the bond behind, whatever was attached to it, okay? So the idea is here. I'm going to share to a new screen real quick, all right, to a blank screen. All right, and we're going to talk about so what is a common acid that you guys have used a lot of in lab? You guys have any common acids that you've used that you're like, I know that that's an acid?
HCl.
HCl, okay. What's the common base that you guys have used? Hydroxide, like sodium hydroxide? So hydroxide is OH minus, right? Okay, so the base, does the base accept the proton or does it donate the proton?
The base donates.
Nope, the base accepts. My acid donates the proton.
Oh, because they're giving the hydrogen.
Yep, I am taking it, right? So I have the proton acceptor, what is taking the proton, and then that's the base, and the proton donator, which is my acid, right? And we know that HCl, like we said, that's my acid. So in an acid-base reaction, a lone pair is going to grab the proton like that. Does that make sense?
Mm-hmm.
Okay, when it does that, is it taking both the bond, I don't know why it does that sometimes. Is it taking both the bond and the atom, or is it taking just the atom?
Atom.
It's just taking the atom, right? It is just taking the proton. Real quick, you guys are probably saying, why do we say proton? What is in a hydrogen atom? Subatomic particles.
A proton, a neutron, and an electron.
Nope. A proton and an electron. That's all a hydrogen has. So if the hydrogen, like you told me, leaves the bond behind, does it have any electrons anymore? No, it's leaving the bond behind. So what's the only thing left then?
Proton.
The proton. That's why we call them protons in acid base. We're just taking the nuclei of the hydrogen, which only consists of one proton. That's why we say proton. Does that make sense to you guys? So when our base grabs the proton, we are leaving behind our bond. Our bond goes back onto the atom that it was attached to. So now, after this happens, this oxygen, right, still has this hydrogen here. It has a lone pair, and this lone pair, but now it is bonded to this hydrogen like that. Does that make sense? Okay, so what happened, and let me erase this here. What happened to that bond? That bond went back onto the atom. What did it become? When you put a bond onto an atom, what does it become? How do we represent
Cl
it?
minus.
A lone pair. So it had these 3 lone pairs already, right? And now that bond went back onto the atom. And so like you just said, right, now this is Cl minus. This was OH minus, now this is Cl minus. We must always conserve charge when we are dealing with molecules. Does that make sense? Charge is conserved, it's universal. If I was to take the charge, Bella, I'll ask you this question. If I was able to somehow take the charge of every species in the entire universe, what do you think the overall charge of the universe would be?
That's a great question. Wait, what do you mean?
0. Everything balances out.
Oh yeah, okay. So I thought
Charges must always balance, right? But in this case, the before, the overall charge is minus. The after, the overall charge is minus. Charges must always conserve. Do you see that? This is one of my principles of mechanisms, whether it's arrow pushing or if it's for resonance. Whatever it was before overall charge has to be the same thing at the end. Are you okay with that? Are you guys all okay? Do you understand acid base a little bit better?
So just to make sure for the problem that's on the test, I
Mhm.
mean on the practice exam, the nitrogen is grabbing the hydrogen, and then the bond over there is becoming a lone pair. I just want to make sure I'm understanding that right.
Yeah, we will do that again real quick here since we have more space.
Okay, I'm sorry.
No, this is why you're here. I'm trying to teach you. If it was an issue, if it bothered me, I wouldn't be spending my evening doing this. Don't think you're wasting my time. I want to be here. You have a nitrogen with a negative charge, right? If you see a nitrogen with a negative charge, you know that it is going to be a nitrogen with 2 bonds and 2 lone pairs. This was something we went over in Gen Chem, and I was trying to get you guys to memorize that. For those of you that were taking organic, is that always know that if you can predict what the charge is, you can know what's there. Then we had this. Then we had our alkyne like this, right? And so I'm going to draw the hydrogen that's coming off here. Okay, so when we do this, what did I just say you need to have in order to have an acid base? What actually makes something a base? What do you need to have to grab a proton? What does my nitrogen have that the other compound does not?
An
A
electron.
negative charge?
Nope, lone pairs.
Lone pairs, that's right.
Oh.
You need to have a lone pair on that atom to act as a base, okay? So question for you, if this is a neutral, again, why does it keep doing that? If I had a neutral compound like this, could this act as a base? Are there any lone pairs on any of those atoms? No, so it can't act as a base. Could this act as a base?
Yes.
Yes, because my oxygen has a lone pair. If you have a lone pair present, it can act as a base. All right. So now, this is why the left, this is actually a very well-known base. This is diisopropylamide. Typically, you have a lithium with it. This is one of the strongest bases you can use. When you continue on in this semester, you will come back to this. But essentially, my lone pair is going to come and grab this proton like this, and this bond goes back onto this carbon, right? I don't take the bond with me. It stays there. Does that make sense? So now, I still keep that lone pair there. But now that other lone pair grabbed a hydrogen, it formed a bond. And now here, I have a lone pair on this side. What am I missing from this picture?
Charge.
Charge, right? So the charge was on the left side, now it's going to be on the right side. And just to be sure, this is a carbon. Carbon has 4 valence electrons. It has 3 bonds and 2 lone pair electrons. That equals -1. That's the formal charge calculation, so that should be -1. Does that make sense?
Yes.
Okay. Who is your tutor? Who must I hit?
His name's Jordan. He works at for NAU.
What a mook. Okay, but do you feel comfortable seeing this now?
Yeah.
How do you guys feel about acid-base reactions now? Do you understand the arrow pushing? A lone pair is always going to grab a proton. It's going to take it, and then you're going to form a negative charge, right? Or whatever on that. Does that make sense? Okay. So now, going back to our problem. When I have my conjugate acid and base, right, I'm going to have, so we said the pKa of this one was 25. What's the pKa of my conjugate acid now? Anyone know?
I think it's 38 to 40 or 40.
38. We can say 38 on the low end, so that's fine. So now, which way is my arrow pointing? To left to right or right to left? Or you guys have no idea?
How did you get 38?
Memorized it?
Oh, right. Is this what it is?
That's correct.
Okay.
That's fine. Don't worry about it. It's just know that that's what that chart's for, right? It tells you what the exact. So when I figure out which way my reaction is going, is this one going from the left to the right or the right to the left? Or you guys have no idea?
I think it goes from left to right.
Correct. Your arrow should be going left to right. So that means that this side is favored. So
Is that because the nitrogen is stronger at pulling hydrogens than the conjugate bases?
So yeah, this is basically it. Your arrow should point from the stronger acid to the weaker acid. That's an easy way to tell it if you get confused. So you go from the lower pKa towards the stronger pKa, the lower pKa to the higher pKa, right? And remember, the lower the pKa, the stronger the acid. Does that make sense? Are you guys okay with that? All right. Explain why HA is more acidic than HB. Include resonance structures in your answer. So if it tells you to include resonance structures, why do you think HA is going to be more acidic than HB? Any idea?
I thought like, I don't know if this is right because my tutor helped me with this, so I don't know if it's right anymore, but he basically told me to look at HA because it has like double bonds closer to it. And I just kind of thought like, I don't know. I just think HA is more acidic, and that's the only reason that I have.
That's correct. So the key is that they tell you resonance structure. So if I had my base come in and remove the proton, I would either have this here, where I have this lone pair like this, or I would have a lone pair here, right? Do you see where I just put the lone pair where that atom took it?
Yeah.
If I wanted to do resonance on the left side, I could move to the left like this to a new resonance structure, or I could go to the right to a new resonance structure. So I could form 2 new resonance structures. So I have a total of 3. So basically I could have this here. Or this there like that, right? If I do it on the one on the right, I could go here, and this can go here. And that's it. So which one has more resonance structures? If I remove HA or if I remove HB?
HA.
The more resonance structures you can form, the more stable your molecule is. Does that make sense? Resonance gives you stability. The more resonance forms that you have, the more stable you are. The more stable you are, that means it's easier to remove that proton. Are you guys okay with that thought? Bella, how are you doing with that?
It makes sense.
Okay.
I'm just writing if I look confused.
No, I just want to make sure. I want to make sure that everyone's with it. Matt, how's it going?
It's going good. I think I understand that.
Resonance gives stability. The more resonance structures you have, the more stable your molecule is. All right. So that's why when I deprotonate HA, I'm going to have 3 resonance structures versus if I deprotonate HB, I'm only going to have 2. So since HA gives me more resonance structures, that's the more stable one. That's the better proton to take. It's the more acidic one. Make sense? Okay.
Yeah. So what you did, just so I like get it in my head, what you did for this is you saw how many resonance structures you can make with just HA and then how many with just HB.
Correct.
Okay.
And whatever one gives you the most, that's your most acidic proton. Okay. Circle the most acidic proton in each of the following compounds. Chop, 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 chop. You guys are slow.
Did you ask us to solve these?
Yeah,
Oh,
I'll let you guys work on it a little bit. While you guys are doing that, I'm just going to scroll down real quick because I'm curious to see how much more we have left. Nomenclature and stuff. Wow, this is how long your test is?
It's 20 questions. She didn't say how many parts each question would have, though.
This would have taken me at least 5 minutes.
We're
no need to flex.
Some of us are just learning this, you know?
Just the advice I'll give to you guys is just get the answer right. Right? Don't miss any points.
That's like what I tell myself before I started.
That's some sound advice right there.
Yeah, I'll just do that. Thank you.
I always think of The Office. I'll ask myself, would an idiot do this? And if he would, I don't do it.
If he would, I do not do that thing.
Yep. It's almost that time. We have just about 2 minutes, for the time limit thing. But thankfully, we will finish this on our next run, and that'll be it. So we have about 2 minutes left. So when this ends, I will open up a new one and we'll finish out. And then next time we do this, I'll just have one of you guys open up a thing. So like the next exam or study session or whatnot. So we'll do that next time.
Wait, the Zoom's gonna end in 2 minutes, you said?
In about a minute.
I have.
Are you-
Oh yeah, I have. Since I'm a student worker of NAU, like my Zooms can stay open as long as I want. So like next time I can open it.
Yeah, and then you can just make me a co-host. We'll do that, but we should be able to finish this on this next little go about. Yeah, so basically same code once it's done. So you guys just go through and do that. So. All right, so I'm gonna end it right now. I'm gonna go grab myself a Coke because I'm thirsty. And so then I'll come back and open it up and we can keep working on these. You guys are doing pretty good. Don't fret, you're doing all right. I'll see you back in a minute or two.